everyone. So I want you to imagine something. I want you to imagine that it's early morning and you are dying for your caffeine before work and you're going to Starbucks to get your double espresso shot. And what you see is that there's a very, very, very long line. And you are at the end of the line, but you are a very, very patient person because you need your caffeine. So you eventually get to the front of the line, and this is what you experience. What you see is the cashier gets the order from the customer, and then walks over to the barista and repeats the entire information over to the barista, and then waits until the barista steams the milk, makes the espresso, puts it all together with your specification of foam on top, and then walks back over to you, gives you your espresso drink, and then gets the card from you, charges you, and then moves on to the next customer. I don't know about you, but that would make me very angry. But when we write software, oftentimes that's kind of what we do. We have two services that might belong in different contexts. And when we want information, we kind of have this synchronous type of communication. We go back to the other service and say, hey, give me this information. And then we wait, and then get back the information, and then try to proceed with whatever we need to do. So in this sort of model, you are coupled. And this type of coupling is called temporal coupling, where you are coupled in terms of time, where you have two services where one service cannot proceed with whatever it needs to do until the other service has completed its operation. So this is sort of bad because now think about when the barista service is down. You can't proceed with charging your customer because you're blocked. And so in this type of scenario, when one component or service goes down, your entire system becomes inoperable. And this is not the sort of things that we want. So even though we could have nice bounded contexts where we've separated cashier operation or barista operation, if we have these sort of service calling service in a very synchronous way, you could end up in a type of system where when one service goes down, the entire system is down. So how do we solve this? Well, Starbucks has the answer, of course. So in Starbucks, when you go to the cashier just takes all the information about the drink that you're trying to order and then writes it in this cup. And then she then places that cup on the table for the barista. The barista then picks up this information, right, and processes, and whenever the drink is ready, just announces, hey, Indu, your drink is ready. And up until that time, I've already paid. I'm just waiting for the drink. In the meanwhile, I'm checking my Slack or email or messages. I'm not waiting for any of these to happen synchronously. Life is asynchronous. Real life is asynchronous. Lots of things happening at the same time. So we can apply this sort of model, this real world model, to our software. So if we did that, we would still have these two services, cashier and barista. But now these services, what they do is they process a message. So when the customer places the order drink comes in, and it processes it, and then publishes an event called drink has been ordered. And this message, the barista is interested in this message. So the barista listens to this message, and that service processes that message, and then publishes another event saying drink is now ready, which the customer or whatever party is interested now receives that event and processes this. Now, in this model, if you're thinking about software services, any of these services could go down. So if the cashier service goes down, it does not impact the barista service. The barista service would just continue to process all the messages in its desk or queue, and when it's done, it's done. The cashier service could still be down at this point. I mean, we have software updates, restarts, and that nature. That does not need to bring the entire system down. So same thing. I mean, if you think about real life, this shift changes. One barista might need to leave while the other one's taking over. That doesn't stop the cashier from taking your money. So we can sort of apply these same real life, how real world operates and bring it to our software. And this is what, this pattern here is called publish, subscribe. And there are several other patterns described in the Enterprise Integration Patterns book by Gregor Hoppe and Bobby W. Also, Gregor has written a great post about why Starbucks does not do a two-phase commit, for those of you that are technical. So there are a lot of patterns that we can mimic from the real world in order to make our software more robust and more reliable and scalable. So, I mean, talking about scalability, if there are a lot of customers, now all you need to do is scale up this cashier service. And you don't need to touch the barista, but just by scaling up the cashier service, you can service more customers. Same thing, if there's a lot of drinks on the queue for the barista, you can scale up the barista and service your customers faster. So this model allows you this flexibility, and in this model, you get reliability and scalability to go. Now, this style of modeling things is called event-driven architecture, where our goal is to make our software services and components talk to each other just like the real world does using messages. So where these messages from all these different software components, they need to go from one software component or one service to another. So you need this sort of bus or a transport that would carry these messages and deliver these messages to the whatever component that it needs to go. So you've got several options. You've got technologies like RabbitMQ. If you're working in cloud, you've got Azure Service Bus and so on. So you've got different options which give you this fundamental thing. So queues are nothing but the messages need to be stored in a durable location, because when services go down, we don't want to lose these very important messages. So the queues give you the ability to store these messages in a durable way. So those are the queues. So we can still take this real life concept and with all this technology available to us, build software in a way that can communicate, doesn't have to be on a loop or a pole, but it could be very event-driven based. When something happens, the software expresses that change, that state of change as an event, and that event could be listened by other components, and then they react to that change. Just like when the barista called out my name, I was doing something else, but I react to that change. I listen to that event, and then do what I need to do. It's the same concept. So when we're trying to communicate between these services using messages, there's two important types of messages that have special intent. So we classify them as commands and events. A command is something, you can think of a command as a message that is sent explicitly to just one service or one party. Whereas an event is like a broadcast. It's a thing that's published, and there could be several subscribers who are interested in that message that want to listen. Now, the interesting thing about commands and events is an event is something that's immutable. It's like a statement of fact. it can't be changed. So therefore, when you publish an event, you only publish it like after the fact, after you're certain that this happened. And you do that because there could be several downstream processes that rely on this. You can't go back to them and say, oh, I'm sorry, that never happened, or, there would be chaos. So you want to publish events after the fact. Commands, on the other hand, they carry intent, and it's so it can. The interesting part about commands is commands can fail. So it can fail for a business reason, not just a technological reason. So commands can fail. I can say, hey, charge this person's card. It can fail because the person didn't have enough funds in the account. So what do we do? And so when we communicate using commands, we have to think about all these constraints. Why is this command failing? And if it fails, what are the compensating actions I might need to take? So the business might have a policy where if you're like Amazon, you're trying to order a book and it might have gone through, but then you get an email like a day later because when they tried to settle the funds on the credit card, there wasn't enough funds. So you get an email now saying like, hey, your order that you placed, we couldn't charge your card. Could you please update your order info with the right credit card information? So this sort of thing, like where we have policies where, or compensating actions, we can design our software by asking these questions when we're designing our software components, especially this communication bit. When we're sending this command, what are the reasons that this command can fail? So if it fails, how do we need to compensate them? So this is where it gets interesting, right? If we are just architects and programmers, we may not have all the relevant information. We need to have these sort of conversations with the business, the domain experts. They know what to do. So they can just give us this policy of like, wait another day and try to charge the card again. Or they might say, well, if that failed again, then you might need to send them this reminder email. We can't make those assumptions, or we can't make those decisions. So how do we go ahead and write our software in a way that it makes sense for the business? Let's just take an example. Let's say we have a requirement. This is like when the aircraft type is changed, you're flying somewhere and you have a reservation. So I flew from LAX to Amsterdam. So for some reason, if KLM decided to change the aircraft type from Boeing, whatever, 787 to 777 or something, then they need to notify me, or this is their policy, where the passenger gets notified, and they have an option. They can either accept the new proposed booking, or they can cancel the flight. So it seems like it's a very, very simple requirement. So if we just, as software engineers and architects, try to design this, we might come up with a design, and that might be okay, but we might miss out very important details. So we can use a technique like event storming, like what Kenny mentioned, and there's several workshops and talks just focused on event storming. But event storming is a super nice collaborative way of trying to figure out what the constraints are, and where you're collaborating not just amongst like architects or leads, but having the right relevant people like business experts in the room. So on the outset, the requirements looked super simple. All it said was like, hey, go and notify this passenger, and passenger, if he cancels, give them the money back. Otherwise, this is the proposed booking. But you've got questions like, hey, what if when we send the email, the passenger doesn't respond? How long do we have? How long should we wait? And what if the passenger had paid for an exit row seat, and in the new aircraft, the capacity is different, and we can't offer that exit row seat, then what? And what if there are like three people in the party that's traveling together, but because of the capacity, we could only seat two. We can't just like tell one person like, okay, which one of you can't go. So we can make all these assumptions in the software, but then we would be building something entirely different from what the business wants. So for a business to succeed, all stakeholders must work together. And our goal as architects and team leads and programmers is to write the correct software. So in order to do that, we have to work with domain experts and business experts to try and find out what these constraints are. Because if we don't have these conversations, then it would be very difficult for us to write the correct software. So a business process, when you take it and when you try to model it as bounded context and use events and commands to communicate, it can be triggered by a bounded context. One bounded context can publish an event that can be consumed by a different bounded context. So when you're looking for how do I name these events and what are the interesting events, you can try to listen for when or whenever in the statement by business domain experts. So when they mention when something like this happens, that's your key or cue for, hey, here's an interesting event that we should take care of. So when we're trying to name these events, oftentimes as when dealing or having written software for years, we're so used to the CRUD mentality. So we often tend to name things like customer was created or customer was deleted. Like if only we could create customers, that would be very cool. But maybe the right business term is customer was onboarded. So these are the right terms that the domain expert might be using, and we want to bring those language or that language into our code and into how we name our events as well. So you can have a business process, and several messages could take part in this business process. So so once once a bounded context receives an event from a different bounded context, it can send commands, it can publish events, and so on. So all these messages together form this business process. And there are other patterns like the Saga pattern, like the several messaging patterns around to help you build this sort of business process using events and commands. So now what happens if we take this requirement and say the requirement changed? And say that the requirement is now, hey, we're going to do this process only for our platinum customers. Now what? In the previous case, it seemed somewhat simple, where something published an event, aircraft changed, and all of the changes that we were doing were in the booking context, like seats, aisle seat, whether we have seats or not. Everything seemed to be like in this one nice area. Now all of a sudden, like we just have this requirement that says like, hey, we can't do this for every customer. We want to do this only for premium customer. So the booking context may not have that information of whether a customer is premium or not. That data or that rules might belong in a completely different context. So now what? So we just talked about like how trying to get data synchronously from another context is bad, and that could bring that has impact on reliability. So in order to make autonomous decision, again, we can use the same pattern, the publish-subscribe pattern, where the flight context might just, or the loyalty context might just publish events. Whenever a customer becomes preferred, or a customer lost the loyalty status, it would just publish an event. And then the booking context listens to that event and stores that information locally in its own persistent store. So now what happens is, like, when the flight planning context publishes the aircraft has changed, we don't have to go to the loyalty context to query to figure out if the customer is preferred or not. We just have that information in our local store. So we've like completely disconnected having to go back to another context to query for data. So what allows for this sort of method is working and dealing with events. So now your, like, whatever component or service that's inside your booking context, that's you know, the decision making component for however you need to apply the rules for rebooking, can just go ahead without having to depend on the loyalty context. So this allows where you can make changes to the loyalty context and not have to worry about bringing the whole system down. You could just have, you know, booking be entirely independent of loyalty. Same thing, vice versa. So in closing, I want to leave you with 3 things. Writing code is the easy part. Collaboration and communication with other people is the most difficult part. And so try to do a lot more of event storming if you are not already doing it. But the key is work closely with the domain experts. And in order to succeed as a company, we have to work with each other. And that means trying to understand what the constraints are, what are the features that we're trying to build. And we have to get this knowledge firsthand from the stakeholders who know this information, so we can write the correct software with all these assumptions correctly. So the other thing is, all models are wrong, but some are useful. So when we go ahead and event storm and come up with like a model, it doesn't have to be 100% right. We can always go back and change it. And this is what we have to do. And it's important for the business to understand that as well. And if you come up with an initial design with an event name, but then you hear that that's not the right word that was used by the domain experts, let's go and refactor our new knowledge now that we learned about the domain back into our code. And that's how our software is going to align with the business. If we don't do that, we are going to have like our software slowly diverge away from the business model, and then making changes becomes more expensive. So refactoring constantly and applying our knowledge as into our code, into our models is super important. And lastly, strive for autonomy. And the way you do it is by using messaging and an event-driven style of architecture. To me, combining domain-driven design principles with event-driven style of architecture using messaging as a technology gives you the best of both worlds, where you're not only having like clean systems with clean boundaries, but you also have baked-in reliability and scalability. Thank you very much.